For today, I'll be presenting this paper by the title TalkingGaussian, Structure Persistent 3D Talking Head Synthesis via Gaussian Splatting. It was published in CCB 2024. Okay, so first let us see like what's the motivation and like what's the task they are trying to achieve for this paper. So the main task here is given some kind of few-minute speech video, they are trying to generate a talking head structure. So the condition is only the speech in this task. So one of the challenging problem in this kind of task is in order to predict the rapidly changing appearance, it's sometimes very difficult to get those deformed facial features. So in previous like nerve work, like different kind of nerve derivatives try to tackle this problem, but the changing appearance often try to distort some kind of facial features. So by using persistent like head structure, in this work, they try to predict what kind of deformation we need to apply on this like canonical, like consistent mesh in order to generate those changing appearances. So using this persistent head structure and decomposable deformation, the talking Gaussian like outperform or synthesize a more clear and precise talking heads. So I will try to explain more in detail later, but given the speech, they try to deform this persistent head structure in order to generate clear and precise head. So the contribution, we can just divide it into three. So the first one is they perform or they present the deformation-based framework, which means using Gaussian splatting, they apply a smooth deformation to the stable head structure, and this allows them to prevent some kind of distortion in the dynamic area. And the other thing they literally do is upon the qualitative and quantitative investigation, dividing the face part into the face and mouth components, help them to actually refine some kind of dynamic detail on the face and the mouth regions, which address the motion consistency for the accurate mouse motions. And the other one is like they are using a high fidelity synthesis approach, which means they use like lip synchronized 3D talking heads that can enhance like facial details and that can help them in achieving better quality comparing to the like pre-existing nerve-based methods. Previously, people like tried to tackle this problem by using 2D generative models. So they try to like synthesize like lip synchronized videos from the single image. The problem with this kind of approaches is it's not consistent during the like head pose change. So this was the main issue. People also use like intermediate representation technique, which means they utilize the facial landmarks, like 68 facial landmarks and morphable models like 3D model to control the structure. But this can also have a problem when we have like intermediate steps because like the face is continuously changing its appearances. So it's very difficult to capture this kind of subtle differences. Nowadays, people use like Nerve because it's very good at like representing 3D information and also rendering talking heads. But one of the problems with Nerve is with like facial distortion, it doesn't really capture like the dynamic region due to like unsmooth appearance modification. I will maybe add a little bit more information about why this is happening later on, but Nerve cannot fully capture like the appearance change because like the color and the density might jump in the middle of the sequence. So like I have some kind of problem with this approach. So since this paper used like 3D Gaussian splatting as a preliminaries and like let's just look at like what the 3D Gaussian splatting is doing actually, just roughly. So 3D Gaussian splatting is basically a way to represent a scene using Gaussian primitives So each Gaussian primitives have a certain kind of property. So they have center, they have scale, rotation, opacity, and color features. So during the optimization time, we're trying to optimize the Gaussian parameters using gradient descent. And using, in this process, what we do is we do densification and pruning to manage the Gaussian counts and details. So this image is taken from the original papers. So let's just see the overall process here. So first, given any kind of image, what they do is they try to use structure from motion points. We can use like, for example, Colmap open source method in order to, given some kind of image, we can just get like a rough point cloud of a given image. And we initialize the Gaussian primitives using this structure from motion points. Because like rather than just like initializing the 3D Gaussian like without any kind of condition, it might be better if we have some kind of rough representation of the image. And like after that, we try to build like 3D Gaussian based on those points we get from the structure from motion points. After that, what we do is you have some kind of camera viewpoint. So we just try to project those Gaussian primitives into the image plane using a differentiable like tile rasterizing. So after they do the projection, so they try to calculate like what's the difference between the projected image and the real image, and they try to do some kind of gradient flow. So on this gradient flow, one of the important things is like adaptive density control, which means if the Gaussian, the 3D Gaussian is underfitting, they try to do densification, which is they clone the Gaussian. If it's overfitting, they do pruning, so that like the Gaussian, it's fitting the particular space that is needed to rasterize. So using this approach, they try to reconstruct or they try to represent a 3D scene using Gaussian's primitives. So let's just see how they use this method on their paper. So the problem setting they have for talking head synthesis is, what is the aim? Let's just look at the aim. The aim is to develop some kind of audio-driven framework that like uses or that utilizes the 3D Gaussian for synthesizing high-fidelity talking heads. So for the training data, they have like a few minutes speech video, like from 1 minute to 5 minutes of a single person from like the center view. And they use some kind of 3D morphology model. Why? Because they need to estimate the camera position of that like that specific frame. And after that, what they use is the audio feature extraction. So they use already pre-trained tool like deep speech model in order to extract like, the audio features. So using a few minutes speech and camera position and some audio feature, they try to synthesize the talking head using Gaussian splatting. Okay, let's just see the overall pipeline they have. So the first thing we can notice immediately is like they have two kinds of fields. So the first field is like persistent Gaussian fields, and the second is like grid-based motion field. So the reason why they need like two kinds of field is this method believes that in order to represent a continuous change, one way to present a continuous change is like using deformation or using some kind of offset prediction rather than just predicting the change immediately or independently. So what they have here is given some kind of persistent Gaussian field, they can get this persistent Gaussian field using 3D Gaussian splatting, just like vanilla 3D Gaussian splatting can give us some kind of 3D mean force field. So what they try to do is like given some kind of 3D canonical pose of human face, they try to predict what kind of offset that we need to have in order to map to the speech audio features. So what they do is like this is persistent, it doesn't change. Like this is a canonical like mean force shape across all the frames. They try to take what's the average shape across all the frames and this is the representation of it. And what they do is, given this representation, what kind of offset do we have to predict in order to match the speech audio features? So here, using grid-based motion field, what they do is using MLP, they try to predict the scale, the rotation, and the initial position of those Gaussian primitives. So they try to say, if we can somehow predict the change that we need to apply for each Gaussian, we can easily render the final synthesized TalkingGaussian. So, and the reason they're using like two kind of branches is, as I discussed before, it's possible to predict the motion field using just one persistent Gaussian field, but I will try to show some qualitative and quantitative results, which suggest that if we actually decouple, or if we separately model the deformation of the face and the mouse region, it actually performs better. Because if we use the single approach, the Gaussian change that we need to apply is very wide, and it can change the reconstruction quality. So rather than just like applying all the Gaussian change in the whole face area, they try to focus, okay, what are the change we need to do on the face branch? What are the change we need to do on the mouse, inside mouse branch? So given this kind of decouple approach, they actually have a better reconstruction or synthesis quality. So yeah, so here they give like some kind of audio features on both MLP, and they try to predict what kind of change we need to apply on the persistent Gaussian field in order to reconstruct the face. So what are the components? As I explained before, like they use like two components. The persistent Gaussian components, which helps to maintain like a stable head structure, which doesn't really change across all the frames. And they also use like a grid-based motion field that predicts some kind of deformation for dynamic facial change. So mathematically, they formulated using like this. So this grid motion field will take some kind of initial position and audio features and some kind of like expression. And this C is the condition. C is the condition they provide. In this case, the condition is the audio, primarily the audio. And using some initial position, then the MLP is trying to predict some kind of change that needs to apply on the persistent Gaussian field. So the deformed parameters are the position, the scale, and the rotations. So this is the deformed parameters. This is the initial position, the initial scale, and the initial rotation. So what MLP predict is what kind of change we need to apply to the initial position, what kind of change do we need to apply to the initial scale value and the rotations. So this is the deformed parameter they try to predict using MLP. So the rendering process would apply the deformed parameters to the Gaussian primitive. So we apply each deformed position, if deformed scale and deformed rotation to each Gaussian primitives, and we rasterize the deformed Gaussian to generate like a target image. So one of the things I didn't mention on the pipeline is they use like incremental sampling. The reason is like they use incremental sampling because it is very useful to stabilize deformation learning by progressively introducing a complex motion. So if we just like randomly sample for example, the time frame 1 and the time from like 10's time frame or like 20's time frame, the amount of deformation that we need to apply is very large, which means when the MLP predicts some kind of deformation, if the target deformation, if the predicted deformation is very large, we have like a vanishing gradient descent, which might fail to update this Gaussian field part. So in order to tackle that problem, they try to sample like sequential rather than just like sampling across multiple frames. So this is a way of like stabilize the learning process. This is the qualitative result they have in order to show like the deformable Gaussian primitives they have. So the reconstruction facial motion here is represented by the deformation and appearance modification. So here, from the initial position, they try to track like uh, how is the dynamic change across position. So let's see. So on the upper side, you can see the offset trace, like they try to trace how the point change frame by frame. So from A to B, B to C. So the thing they want to show here is the change from A to B, B to C is continuous here because they are trying to track the deformation from one frame to the other frame, and which is easy to do if we can track the offset of like, and we can just reconstruct that by adding or subtracting the offset. And also here they try to also track the color trace or like how the color changes across multiple frames once we move from the initial point to the final point. Okay. So yeah, so as I introduced before, on this paper, they are mainly using face and mouse decomposition. One of the motivation for this approach is motion consistency. So using a single field motion can cause some kind of distortion between face and inside mouse region because speech is more targeted around like mouth and lips. So, but like we also have to change some kind of expression for our face. So rather than just tackling all the changes like using a single field motion, it's better if we have like separately dedicated branch or deformable Gaussian in order to capture like the differences between the face and the inside mouse branch. So they use like two deformable Gaussian field for each branch. So for the face branch, it just model some kind of facial motion, excluding mouth. And for the inside mouse branch, they specifically handle only the dynamics of the mouse movement. So like each branch doesn't interfere with the other. So it's just like separate way of decoding the deformable Gaussian field. So for the face branch, this is how they model using some kind of MLP. The input is the audio and the upper face expressions. So given this input, the MLP will output some kind of prediction that needs to apply on the mean persistent head. So on the inside mouse branch, once again, they give some kind of deformation prediction using MLP. It's pretty straightforward. They give the audio features, and given the audio features, the MLP will just predict what kind of position that we need to add on the initial position that we are given. So for the rendering, since we have like different branch, so they have to have a way to combine or to synthesize both the mouse and the face branch together. So in order to do that, like we have to also make sure the color values are like blending together. So this is for the face and this is for the mouse. So they just like add it together to render the final like high fidelity image. So A is just like opacity. So they try to blend like the opacity value between across the face and the mouth. And just this is just a way of like fusing both the branches together so that they have the final rendering. You can see from here. So this is like separate kind of rendering they have. So once they have the face value and the mouth value, they try to just like render it together, like synthesizing high fidelity image. Yeah, so the benefit of like having face mouse decomposition is it enhances accuracy. So it precisely allow them to map the precise movements without like affecting the overall face structures. So this is like the qualitative result of like the effect of like face mount decomposition. So this is the ground truth. This is using just a single field without using some kind of separate branch. This is using separate branch. So using the decomposition, it's more aligned with the ground truth because like lips and like inside mouth are, especially like teeth, are very like difficult to map only using a single field. So in order to like, address that problem, if we have dedicated mouse branch, we can like tackle this kind of problem. The model, like the single field, also it's also good in terms of generating like synced result, but like it might be better aligned if we use like mouse decomposition. So this is just like some qualitative result of how face mouse decomposition really helps in reconstruction at that time. So yeah, so the training setting is very interesting. So so for the training setting, like they have like three different like stages they apply. So for the static initialization, on this stage, the main objective is just to establish a force head structure. So as we talked before, for this paper, they use like some kind of representation of force head structure that they can apply some kind of offset. Right? So to establish that initial static head structure, they initialize persistent Gaussian field using vanilla 3D Gaussian splatting. This is the function. So in order to have this static initialization, what they do is they try to calculate like, the pixel-wise low and lows and the structural similarity between the constructed image and the ground truth image. So the next stage is in trying to set up the training stage for the motion learning. For the motion learning, the objective is here is to learn like the dynamic facial features. So they are trying to integrate motion field with like predicted deformation. So in this case, it's similar, but it's just like predicting the dynamic facial motions. So for the fine-tuning time, they fine-tune the color parameter and they try to fuse the face and the mouse branches, as we discussed before. So on this part, they use the pixel-wise low and lows and structural similarity lows. And they also use like perceptual similarity in order to capture what's the perceptual difference between the reconstructed image and the ground truth image they have. So optimization strategy, the loss component, they use like a low and lows for to measure the pixel-wise difference between the reconstructed and the ground truth images, and structural similarity to assess like structural similarity between the two reconstructed and ground truth image. Also, we have perceptual similarity. So one of the interesting thing is like the training time it takes in order to train all this training stages. It just takes like 0.5 hour per portrait. Like if we have training data of like 1 to 5 minutes, we can train all this training stage using like 30 minutes. That's one of the most interesting part of this paper. And yeah, for evaluation matrix, they are using quite a lot of evaluation matrix. So they divide it into like 4 different kind of parts. So for the first part, they try to assess the like what is the static image quality and the dynamic motion accuracy and the facial expression accuracy. Also, in terms of efficiency, how are their model performing comparing to others? So for static image quality, they use like signal to noise ratio, perceptual similarity, the one we discussed before, like structural similarity. For the dynamic accuracy, they use like, since in dynamic motion accuracy, since the face changes smoothly, they need some kind of quantification in order to like track those facial landmarks movement. Also for the like speech, they use like synchronization confidence score, which indicates like lip synchronization accuracy. The higher the confidence, the better the accuracy. Also, they use like synchronization error distance. The lower the error distance, the better. So they also use like facial expression accuracy. So for this one, they divide like what is the upper face action unit and the lower face action unit. So action units are a way to quantify the facial expression. So for this accuracy, they use like 7 specific action units. For example, one action unit can be how well our eyebrow rises or like falls. So depending on the how much we raise our eyebrows, like they give some kind of score. So first, like this metric will detect the presence or the absence of like the raised eyebrow, and it just gives some kind of intensity measure from 0 to 5. So using those matrices, they try to quantify the facial expression. And yeah, one of the interesting is like efficiency metrics in terms of training time, which I described like it takes like 30 minutes. And they also like FPS is very high. All right, so this is the quantitative results they provide. So across all the rendering quality and motion quality and efficiency, we can see they outperform all the previous existing works. Mostly they comparing with like nerve derivative works usually. So one of the things we can notice right away is like the training time. Like comparing to other model, the training time is like extremely less. And as you can see here, the FPS is very high because it's very fast. Like they're using 3D Gaussian splatting in order to like represent and render back for their talking head. So this is also like lip synchronization settings. So in these settings as well, they are more aligned with the like speech and with the mouth and inner teeth part. So for example, for Obama in May, the AR is very low, but the confidence is very nice. Yeah, this is just like some of the results they have. And this is some qualitative results. So one of the previous problem of like nerve is doesn't really capture like the dynamic detail that is happening on the mouse area, because like nerve fails to capture like the smooth change or the continuous deformation of a given talking face. So, but like using their approach, especially using decouple like mouth and face approach, they are better capture the continuous change or the smooth transformation of a talking video. Yeah, so the conclusion is like the talking Gaussian use deformation-based framework. This is very important because this deformation-based framework allows them to utilize 3D Gaussian splatting for synthesizing high fidelity talking heads. And they also like present their decomposition and how does it affects the overall reconstruction quality. So this face mouse decomposition highly addressed the motion inconsistency that we saw from the previous works. And the efficiency of their training is very impressive. So they take like 30 minutes per portrait using RTX like 3080 GPUs. And one of the main takeaways is like this approach is possible because of like the deformation-based approach. So instead of just like directly predicting the point, they try to predict the deformation-based approach, which means on how do we leverage smooth deformation given some kind of canonical persistent head structure that minimizes like distortion and maintains like the facial fidelity that we need. Yeah, so this is for me. If you have any questions.
Yeah, this paper is quite working very good, and Juno also used tuning this for some his own. Yeah, it's very fast to train.